Hi, welcome back to this channel, folks, and today we're going to be going over two types of movement inside of Unity, one regarding transform movements and the other regarding rigid body movements. These are two very important things you need to understand before creating any kind of game inside of Unity. So let's go to the computer and show you exactly what I'm talking about. Alright, so I went ahead and created a scene with game objects from a Unity tutorial about how to use Unity's Pixel Perfect camera, so you can go to the GitHub link in the description of that video to get the look of the scene I created. I also created a new scene and copy and pasted some of the game objects from the demo scene and placed it in the new scene I created. I also duplicated the ground object to create a platform for some example purposes. Now there are two things I want to point out before going any further that I feel are important when coding for movement. Number one is the order of event functions in relation to when Unity handles physics. A great reference for this is this flowchart found in Unity's documentation, and this is something I highly recommend saving somewhere for reference, as you most likely will need to come back to this throughout your game development progression. The two functions we will be dealing with today, however, are the update and fixed update methods, which you can see here in the flowchart. Make sure to notice that the fixed update occurs prior to Unity's physics calculations. This is extremely important to remember carrying forward. Now on to number two, which is how time works inside of Unity's engine. We access time by calling time.deltaTime, which for update means a time between each frame, as update runs on every frame of your game, but for fixed update it means a time between each physics step, aka when Unity calculates physics, which is on a fixed time step of 0.02 seconds. The fixed time step on which this physics step occurs can be found in the project settings under the Time tab. Now, I'm going to pause here because after doing further research, I noticed something that some might get confused over, which is what time.fixedDeltaTime is. Time.fixedDeltaTime gives us access to the fixed time step value, which as we saw earlier is 0.02 seconds. When putting time.deltaTime inside the fixed update function, Unity automatically converts it to time.fixedDeltaTime. So in essence, time.deltaTime in the fixed update is just equal to time.fixedDeltaTime. This may be confusing, but trust me, it's listed in Unity's documentation as such. The reason for having a fixed time step is to simulate real-world physics, which needs to have a consistent measurement of time, and inside of update that is just not possible, as the time between frames is dependent on how fast your computer or device can process frames per second. And as most gamers know, the time between frames is not always consistent. We have no control over this, and this is why fixed update exists. With this in mind, we need to make sure to put any physics manipulations inside the fixed update function to make sure everything behaves as expected. You can test out the difference in time.deltaTime inside the event functions by using this line of code in your C# script, so you can visually see the difference. Now you may be wondering, well, why not use time.fixedDeltaTime with our physics manipulations inside the update function instead of using both update and fixed update? Well, that's because even though time.fixedDeltaTime is set at 0.02 seconds, update is still running every frame and is not happening at the rate at which Unity calculates physics. It also occurs after the physics calculations, as we can see in the order of event functions. So if you go with the fixed delta time inside the update function, just keep in mind that it could cause bugs or jittery movement due to when and what time Unity handles physics in the order of event functions. Now there's one more question you might ask yourself, and that is why use time.deltaTime at all? Well, for the update function, if we move our player at a fixed amount per frame, that might cause the movement of your player not to be smooth as the time between frames vary. So when we adjust our player movement by multiplying it by time.deltaTime, then if the time between frames is large, your player will move a farther distance, and if the time between frames is small, then your player will move a smaller distance, creating the effect of smooth movement over a period of time. Now for fixed update, even though the function is happening at a consistent rate, you'll still want to adjust by time.deltaTime, because if you decide to change the fixed time step in your settings, your movement will not adjust properly, since both the rate at which fixed update runs and the value of time.fixedDeltaTime are equal to whatever you have the fixed time step set at. Now I know this is a lot of information, and I try to condense it down as much as I could. So if you need to rewind and get a better understanding of what I covered so far, I highly recommend doing so, as it will greatly benefit you moving forward. Alright, now with all that out of the way, let's get to moving our player. So first things first, let's create two player game objects that we will use to demonstrate the different kinds of movement. Now you can use any kind of sprites you would like, but for this video, I will be using pre-made sprites I created using the methods shown in my converting 3D models to 2D sprites tutorial. If you haven't already seen that tutorial, definitely check it out by clicking on the link that should appear in the right-hand corner, or click on the video link down in the description below. Okay, now drag the two sprites into the project hierarchy to allow Unity to create game objects for both your players, and we will name one of them Transform Player and the other Rigidbody Player. Now I'm going to skip ahead a little bit as I want to add text above these characters and add a new material with normal maps, that way we can get a better visual on exactly which player is which. Once that is done, we will need a way to control each of our player game objects, and we will do this via C# scripting. Select the Rigidbody Player game object, then go to Add Component at the bottom of the inspector window and start typing Rigidbody Movement. This will do a search through all of Unity's pre-built components, and if none are found, will allow you to create a C# script with whatever you typed out. Click New Script and make sure that is named to whatever you typed out, and then click Create and Add. Now repeat this process for your other player game object, except this time name your script to Transform Movement. Now we also need to add colliders for both of our game objects, so with Transform Player still selected, scroll down to the bottom and click the button that says Add Component. Type in Capsule Collider in the search bar and make sure to select the 2D collider since we are working in the 2D workspace. Repeat this process for your Rigidbody Player game object. You can adjust your Capsule Colliders to suit your sprites using the offset and size values of the 2D Capsule Collider component. Now that we have our collider set up, there's one last thing we will need to do, and that is adding a Rigidbody to a Rigidbody Player game object. So click on your Rigidbody Player, go down and click Add Component, and search for Rigidbody, and make sure to select the 2D Rigidbody. Also make sure to click Freeze Rotation on the Z-axis of your Rigidbody component. Once that is done, we are now able to start writing code to control each of our player game objects. Let's start with our Transform movement. Open up the Transform script by double-clicking on the script attached to the Transform Player game object. Create a float variable called speed and make sure to set it to public, that way we can access it in the inspector window inside of Unity. Also create a vector2 variable called move. There is no need to set this one to public as we won't need to manipulate this variable in our inspector window. Upon creating this script, Unity automatically creates a start and update function for you. The start method only occurs upon the first frame of your game, and the update occurs once every frame. We are going to go ahead and remove the start function as we won't need it for our transform script. Now that we have our function set up, let's start writing our movement code. We want some way to get our input for directional movement, and we will do this by getting the values of the horizontal input axis and the vertical input axis, which is currently mapped to the arrow keys and the traditional WASD keys on our keyboard by default. You can check this by going to the project settings under the Input Manager section. Now let's set our move variable to the following code inside the update function to get the values of our horizontal and vertical input. Note, when setting a variable equal to something, you need to make sure the variable types match. For this instance, we made sure to convert our input float values for horizontal and vertical input to a vector2 by creating a new vector2 and assigning our horizontal input to the x vector and the vertical input to the y vector. Now we put this code inside our update function because we want to get our input as fast as our machine can handle between each frame of our game, which is exactly what update does. This will allow us to set our move variable to the value of the horizontal and vertical input, which for both ranges between -1 to 1, with 0 meaning no button is pressed. The next thing we will need to do is write code that moves our player game object. For this script, we will be using transform.translate to move our player game object. Now since our movement doesn't require any physics manipulations, we can go ahead and add this code inside our update function. So inside the update function, type out transform.translate, then in the parentheses, put in your move variable, then multiply that by speed, then time.deltaTime. The time.deltaTime is binding our movement to the frames per second, so whatever we set our speed to, our player will move that many units per in-game second. Before we move forward, let's go back to the speed variable and put a default value of 10, that way our player will move at a decent pace. For beginners who may be confused, vector 2s are coordinate points along the x and y axis, and vector 3s are coordinate points along the x, y, and z axis. So now that we have that set up, we can go ahead and click play and notice our player moving around the scene as expected. Now notice that the player doesn't fall to the ground. This is because there are no physics properties attached to our player. We can add physics simulations by either adding code to simulate gravity and other physics properties, or we can add Unity's pre-built 2D rigidbody component that calculates the physics for us. Without the rigidbody component, your game objects with only colliders will not interact with each other automatically. Now, Unity has a powerful physics engine, and it is recommended to use it to its full capacity when possible. But when using Transform to control your player movement, you will limit some of those capabilities, especially when it comes to interacting with other physics objects. Let me explain what I mean. Unity calculates all of your physics properties behind the scenes, and using Transform cancels out your player's movement in those physics calculations, therefore causing bugs and jittery movement when it interacts with certain physics objects or colliders at runtime. Now the question asks, well, when do we use transforms for movement? Well, let's say you want to move an object across a screen and it doesn't interact with any other physics objects, such as a point system. Since we don't want our point system to interact with anything in the scene, we'd want to supplement transform movement instead of rigid body movement. Now before we move on to rigid body movement, it is also worth mentioning that physics calculations can be expensive when it comes to performance, so it is highly recommended to use transform movements when it is safe to do so. Now that we have covered transform movement, let's move on to our rigid body movement. Select your rigid body player game object and double-click the rigid body player movement script to open it up. Now for this script, since we will be dealing with physics, we will want to add the fixed update function. You can do this by either typing it out and having Visual Studio autofill it for you, or by placing your cursor wherever you want to add the function and click Ctrl-Shift-M to open up a window with all of Unity's available functions. You can search for fixed update, then select it and click OK. You can also remove the private from the function, as it's not necessary to make this function private for the script. We will also be keeping the start function for this script to allow the assignment of our rigid body component. That way we can access the rigid body's properties throughout our code. Now let's create a public float speed variable and a vector2 move variable, like we did before, and in this script let's create a rigid body object variable that we can assign a rigid body component to. Now we can access the rigid body component on the game object that the script is attached to by using the following code. But to have the properties accessible throughout our code, we want to set this component to a rigid body variable like such. Since we only need this to run at the beginning of our game, we have added this code in the start function as it only runs on the first room of our game, which is exactly what we want. Now that we have our variables set up, let's fill in the code for horizontal and vertical input, as we will be using this across all types of rigid body movements. This code will return values between -1 to 1, with 0 meaning no button is pressed for both x and y vectors. Now let's get to moving our player. There are three main ways to move your player game object using rigid bodies. The first is Add Force, which, as the name states, applies a force to our player game object. This creates movement similar to how a car moves, where over time the force is incrementally applied. So when we want our player to move based on input, the force applied to our player slowly increases over time. The reverse happens when we want our player to stop, creating a sort of sliding movement as the force slowly decreases over time. Now let's go to the code and show you how we can use Add Force for movement. Go to the fixed update and add the following code. We are not going to be going through all the different kinds of forces for the sake of time, but we will be showing you the basic setup for how to use force for basic movement. We will want to add the following line of code to our fixed update because we want our physics manipulations to occur with our physics calculations. This code is taking the Rigidbody 2D component and using the Rigidbody 2D built-in public method Add Force to apply whatever force we want. We want to add force based on our movement, and the Add Force built-in function takes in a vector2 value, so we will plug in our vector2 move variable into this function. Now we want to be able to control the speed of our force, so we can go ahead and multiply this vector2 by the speed variable to allow us to control over how fast we want our player to move. We will also multiply the speed variable by time.deltaTime, that way the movement adjusts based on our fixed time set value. Now, as I mentioned before, the Add Force method also takes in a force mode, which would look something like this, but since Unity by default sets up the force mode to just plain force like we have currently, we can go ahead and remove this. You can check out the different kinds of forces for both 2D and 3D rigid bodies in Unity's documentation. Now if we click play, the results of the Add Force are shown. If you want to adjust the speed, you can click on your rigid body player and adjust the speed under the rigid body movement script component. Now this can create some cool effects, but may not be the kind of movement you want, so the next alternative is changing the rigid body's velocity. The rigid body's velocity allows you to create more realistic game movement, as velocity occurs at a fixed rate over time. So the player game object's movement occurs immediately upon player input without having to wait for the speed to slowly increase over time like Add Force does. Let's go to our code and show you how to create this kind of movement. Comment out the Add Force line of code, then type out rb.velocity to get access to a rigid body's velocity. Now, depending on what kind of game you are creating, whether it be a Galaga-like game or a platformer, you will use one of the two following lines of code. The first line of code will mainly be focused on platformers. We will set our rb.velocity to a new vector2 and assign the x vector to our x value of our moveVector2 variable, then multiply that by speed, then by time.deltaTime. Then we will assign the y of our velocity to the rb.velocity.y. Now, if you are making a Galaga-style game, then we can implement our yVector2 move variable and times that by our speed times time.deltaTime. You can also refactor this code to look like this for a cleaner look. We add time.deltaTime, that way our movement occurs at the same time scale as our physics calculations, and we use our speed variable to give us control over how fast our player can move on this timescale. You can go ahead and click play to see the results of each line of code. When using the y of the rb.velocity, you are allowing gravity to affect your player's vertical movement instead of the player's input. This is useful when creating jumps for platformer games, as you can add a force to make your player jump upwards on button press while maintaining the physics of gravity. I will not be covering jumps in its entirety in this video, as it is a rather large topic to cover and I want to take the time to explain it thoroughly. I will, however, be making a video in the near future going over how to customize jumps, so make sure to like and subscribe so you don't miss out. Now, when using vertical movement for velocity, you will overwrite Unity's gravity calculations every function call, causing gravity to not work as intended. Since using vertical movement is to mimic a Galaga-style game, you might not want gravity to affect your player to begin with, so go ahead and set the gravity scale to 0 on the rigid body component to fix this issue. Using vertical movement for the y vector with the gravity scale set to 0 would create the results shown on screen. Now, the last option creates almost the same effect as velocity, minus a few slight differences. This option is move position, which moves the rigid body's position without touching any of the physics properties. Now, since you are moving the rigid body by position, it will overwrite the velocity and gravity physics of your player game object. Now, since this is still using the rigid body component, the collision and movement responsiveness behaves as a rigid body would, so it behaves much better than translate movement for moving something that you would want to have good collision detection with. Now, this still is a physics object and still requires expensive physics calculations, so don't completely discredit the translate movement, as it can still be useful in situations where collisions aren't needed. Now type out the following line of code in the fixed update. Here, we are adding the rigid body's position and moving it by our vector2 move variable, and like we did before, multiplying it by our speed, then time.deltaTime. Click play and see the results. As you can see, the move position causes the physics velocity to be overwritten every frame, causing the slow fall to the ground. Move position is not meant to be used with gravity, so in order to completely get rid of the gravity, just set the gravity scale to 0 on the rigid body component. As you can see, this creates a much cleaner look with move position. Now for the conclusion. Now, Add Force, as you can tell, is much different from the other two types of rigid body movements, and is used in specific use cases where responsiveness is not of concern or you're trying to make vehicle-like movement. For quick and responsive movements, velocity and move position are your best bets. But now it begs the question of which one is better between velocity versus move position. Well, like I said before, they practically create the same effect. However, there are a couple of things to be aware of with move position. The first thing is that gravity does not work with move position, as it resets velocity to 0 every time it is called. There's no way around this unless you manually create the gravity physics yourself, but even then it doesn't quite work right, and in my opinion is not worth the effort. Now, the confusing part of this is that in the 3D space with a 3D rigid body, gravity works completely fine. Confusing, right? So my conclusion with this is that this is either a bug or it is an inconsistency in Unity's physics engine. The last thing to consider with move position is that it does not account for other physics properties such as friction, so just know that you can't manipulate friction and expect it to affect movement when using move position. Now, your choice of movement comes down to these factors. If you want to move your player around on the X and Y axis like a Galaga style game and don't require gravity or physics properties, but still want the good collision detection, then use move position. If not, then use velocity. Lastly, here's a chart that gives you a clear breakdown of when to use each, so pause here, take a screenshot, or do whatever you want to do to let this sink in and remember it. Now for our last bit of information as a bonus tip. If you have an issue where your character moves really fast and clips through walls, the best solution for you is to change the collision detection from discrete to continuous as such. As you can see, it greatly reduces the chance of your player clipping through the walls at high speeds. Alright, I hope that gives you a clear understanding of how transform movements and rigid body movements work and when to use each. If you like what you saw today, make sure to hit that like button, subscribe, and tap the notification bell, that way you don't miss out on any new content that's uploaded on this channel. I also have a link down below for Patreon and would greatly appreciate your support. With that being said, that concludes this video, and I will see you guys next time.